Okay, we'll wait for 2 more minutes. The talk will start at sharp 7 p.m. Okay, am I audible?
Yes, Sneha.
Okay.
Yes, Sneha.
Yes, sir. Yes,
Good
sir.
evening.
Good evening, sir. Good evening. So we can begin the session. Good evening, everyone. It's my pleasure to welcome you all to the webinar on the topic Engineering of Rocket Structures, conducted as a part of Aagneya 2022, India's first ever techno, managerial, entrepreneurial, and cultural fest. First of all, I'd like to invite the speaker of the session, Mr. Krishnadasan.
Thank you, Sneha. Am I audible?
Next, I welcome.
Okay.
Yes, sir. Yes, you're audible. Next, I welcome all the participants present here on behalf of ICA GECBH. Hope you guys will have a great time. And at the end of the talk, there will be a Q&A session where you can clear all your queries. Then a feedback form will also be provided at the end of the session. Do fill the feedback form, and all the active participants will be provided with the e-certificate. That's it. Thank you. Thank you very much. Now, Krishnadas sir, over to you.
Thank you, Sneha. Just a
Yes,
minute.
well,
Just a minute.
Okay, sir.
Good evening, everybody. And I thank Sneha James for giving me this opportunity to talk to all of you. I understand Aagneya as the forum of fresh engineers to come out of Barton Hill, which is a college of government college of Trivandrum, a sister concern, I would say, of College of Engineering Trivandrum, where I passed out in 1984. Okay, I got a chance for serving for ISRO for nearly 37 years, and I retired last month. And may I start my presentation now?
Yes, sir. You may.
Okay, is it visible now?
Yes, sir. It's visible. Yes.
So today my topic is regarding engineering of rocket structures. Sneha, this is a combination of mechanical, civil, and electrical engineers, right?
Yes, sir.
Okay.
We have all, I think we have all registrations from almost all departments. Yes, sir.
Oh, very good. Okay, I'll try to give a brief introduction about this. Doesn't convey much of deeper engineering aspects, but I'll give you a flavor of what is the topic, what the topic is. Okay. Here, rockets and aircrafts, when we compare, the aircrafts and launch vehicles are designed to minimize the structural mass or the inert mass of these vehicles so that they perform the best. Okay. Usually, rockets are not winged bodies. They are mostly a cylindrical type of simple structures as compared to aircrafts. Both adopt stiffen shell or plate constructions. Stiffen shell is not unknown to all of you. It is something like a monocoque shell, having discrete stiffening or a uniform stiffening according to the requirement. Okay. Now, thrust from the engines or the motors are converted into accelerations, or they are supposed to resist the drag, etc. And accordingly, these vehicles fly. The thrust force in both are a reaction experience due to the ejection of high velocity jets, and aircrafts are usually they are all guided except some of the autopiloted aircrafts of defense. And rockets for launch vehicles in general are pre-programmed autonomous vehicles. They are pre-programmed. They are not deciding their path everything on their own, but there are some pre-programming happening within the computer. Okay. And aircraft generates lift from aerodynamics, and rockets gain altitude from thrust force. They try to avoid angle of attack. What is angle of attack? I'll describe later. Aircrafts have air-breathing engines. They achieve nearly 3 Mach maximum, whereas the launch vehicles achieve somewhere around 15 Mach or 20 Mach. And they go beyond the atmosphere where Mach number has no relevance, because Mach number has got a connection with respect to the local velocity of sound, and sound is not there in vacuum. Okay, this is aircraft Boeing 747, a cutaway section of aircraft. You can see a lot of the initial mass to final mass ratio for a stage is governing the ideal velocity. Here this solid motor has got a disadvantage that the total combustion chamber of a solid motor is having a total motor case is a combustion chamber. So this is solid motor. It has got a grain, solid grain, and the total combustion happens inside this chamber. So structurally it is going to be heavy. Whereas in a liquid stage, you can see there are fuel and oxidizer which are contained with a structural systems. The structural aspects of a hardware, it is the functioning. We need to know what is the functioning. For example, a motor case has to function at 60 bar, whereas the tanks have to function at a much lower pressure. That is one functional aspect. Another functional aspect is the tanks may be containing corrosive fluids. Okay? So that's also a problem for liquid stages. They are corrosive. Okay? And the design environment is the corrosive environment, for example. And capability of the design hardware has to be assessed. Then qualification process it underwent. Because any hardware which is designed has to be qualified before it fly. So flight worthiness should be ensured. So we don't do this kind of qualification for a house, for example, where we live in. We are sure that it is going to withstand every load it is designed for. But as far as a rocket hardware is concerned, it has to be designed and tested. Okay. And deviation analysis. I'm sorry for the wrong spelling there. The ascent loads. That means when the vehicle is ascending, how the loads will be acting on the vehicle. The aerodynamic loads due to forward velocity. That means when it is crossing the atmosphere, Earth atmosphere, for example, it will be subjected to several forces, right? Okay. Due to the forward velocity, there will be side force, lift, drag, as well as the dynamic loads due to aerodynamics and the structural interactions. Okay. Basically, the inertial acceleration due to the liftoff, that is generating a forward acceleration. So to that extent, there will be along axis, there will be a axial load, and side direction, if there is a lateral acceleration, it generates some inertial force sideways. Okay. And the dynamic loads can happen due to the oscillation in thrust, because all the thrust delivered by the propulsion systems, they are not very steady and very quiet, there will be thrust oscillations. Okay. So to that extent, there will be a dynamic excitation to the vehicle body. Then there are transients happening due to the dynamic thrust. Sometimes there will be a blockage of nozzle. In some cases, there are transients like that. Okay. Then there are coupling between the structure and propulsion system frequencies. That is also a problem. Acoustics. Then slosh of fluids. The liquid tanks will be subjected to sloshing of fluids. For example, that PSLV, tank, it will be subjected to sloshing of nitrogen peroxide and hydrazine. Okay, dimethyl hydrazine it is called. So these liquids will be sloshing and will be giving some dynamic forces onto the vehicle. Then thermal loading will happen. These are the environments the structures will be subjected to. Just to define what is lift, drag, and thrust. Lift is in the lateral direction. As far as rocket is concerned, lift as well as side force is in two directions. They are both lateral forces, doesn't really matter as far as a rocket is concerned. But for aircraft, they are well defined. Lift is something which is going to make the aircraft lift upward. Okay, that is a lift, and the side force is orthogonal to lift, and drag is also orthogonal to lift in the direction of the axis of the fuselage. You forget about the discussion about the the equations, what is lifted here. You can forget about that. Now, as far as a free body is concerned, it has got things like this. Okay, a center of gravity, and about the center of gravity, the vehicle is rotating. And when the vehicle is rotating, it has got a lateral acceleration which is generating a rectangular force like this. If it is a uniform body, if it's not uniform, it's not going to be a rectangular distribution. Will be to that extent will be varying. And then if it is a rotating body, there will be a angular acceleration which will be giving a tapering acceleration along the length, and accordingly for a uniform body, the lateral force due to the accelerations, both rotational and lateral acceleration, will be a uniformly varying force along the length. This won't be true for a rocket because it is having a non-uniform distribution of mass. And forget about this equation. It is nothing but the integration of the total forces along the length. Now, the real thing happening for a vehicle is not very simple because it is having a varying geometry as well as varying mass. Accordingly, the forces, both aerodynamic and inertial forces, will be varying, and accordingly the bending moment distribution will be something like this, and shear force distribution will be something similar to this. Okay. One thing I just wanted to tell you is the disturbances due to the aerodynamics will be controlled by a lateral force which is called the control force, so that the vehicle will be kept in equilibrium. See, if there is a lateral force in an unstable vehicle, the vehicle can rotate because of the lateral force and it can brake. This kind of braking only has happened in some of the failed vehicles like ASLV and GSLV. A few of our flights failed because of the lack of control force or no control force condition. So control force is very vital, and this is a life saver for us, control force. Okay. Again, this is a problem. Yes. Okay. Now, these are the quasi-steady loads. What is quasi-steady? Is the fundamental frequency of the system and the frequency of the excitation. If this is high, it is called quasi-steady. Okay, these definitions you will see anywhere. So if the frequency of the system is too high and the excitation is at a very, very low amplitude, you say that the excitation is very steady. And in pressure vessels, motor cases and tank gauges are subjected to pressure vessels. I told earlier, compression, tension, and local loads will be happening. These things are very clear. That means when there is a acceleration, the forward body, for example, when the thrust is developed by the motor case, the forward body will be subjected to axial compression and the rear body will be in tension along with the pressure inside the chamber. Okay. And aeroelasticity, you can just note this particular phrase. It's a Collins triangle. Aerodynamic forces, elastic forces, and inertial forces, they interact to form the aeroelasticity conditions, static and dynamic aeroelasticity conditions. Then the flight mechanics will be defined between the aeroelastic and inertial forces, and the structural dynamics is defined between the elastic and the inertial forces. Okay, these details you will see in textbooks. It's very interesting. Please note this phrase, Collins triangle. Internet, these things will be available. So basically, a structure is subjected to these forces. Just go through this diagram. This is very important for later sessions. Okay. Tension, compression, torsion, shear, and the flexure. Okay. Bending, that is means flexure. These are the basic forces acting on a structural member. There are two types of designs in structure. One is strength-based, other one is stiffness-based. Strength means it has to withstand the loads. Okay, basically that is called the strength-based design. Stiffness means it has to meet some minimum frequency or minimum buckling margin. These are the stiffness-based designs. Fundamentally, the pressure vessels are strength-based designs, but there are cases where it has to have some minimum stiffness conditions also. And stiffness-based designs are something like a spacecraft adapter. Spacecraft should not be subjected to a frequency less than some hertz. In that condition, you have to see that the payload adapter is fairly stiff. Okay. These are the material options we have. Can I just go through this? Maraging steel is M250 grade maraging steel, it is called, the first one. It's a very costly steel. Okay. It has got a proof strength of 1700 MPa, which is more than 4 times the strength of structural steel what we use in our civil construction. Okay. And these two terms, specific strength and specific stiffness, are very, very important in structural engineering. So you will see that in metals, maraging steel is faring the best, 231 with respect to specific strength. Titanium is very close to it. This is a alloy of is pure titanium. 6% aluminum and 4% vanadium are added to titanium to make this alloy. It is also equally good as merging steel. Okay. Aluminum alloy 2014 is a very versatile alloy we are using. That's also faring good. But you can see that here also, this alloy is 4 times stronger than or 5 times stronger than normal aluminum. 480 UTS is almost 5 times stronger as compared to pure aluminum. But when you come to composite, these three are composite materials, you can see the difference with respect to the specific strength and stiffness. They are faring much better than metals. So composites are very good proposals for large vehicles. This is again another way of telling about the advantage of these materials. Just a exploded view of a typical launcher. Okay. Now this stress strain curve of a metal is something like this. This phrase also you please note down, Ramborough's good relation. So this the shape of this particular stress strain curve is defined with this equation. So F.7, it implies the yield strength of a material. It's a proof strength, we call it. It's a secant lines at 0.85% of E and 70% of E, or the Young's modulus, where it cuts the real stress strain curve. These points are defining the F.7 and F.85. With this Ramborough's good relation is worked out in this fashion. So the N is the shape factor for this curve. So this is the construction of such a structure. Now what is buckling? This you have already learned in your BTech earlier semesters. Buckling is an instability. Depending on the end conditions, the critical factor will vary. Actually, pi squared EI by L square is for a both sides hinged construction, but a K factor will come depending on the end condition. K will be 0.25 for a cantilever, and if it is both sides fixed, it will be 4, something like that. So there is a condition. As far as a flat plate is concerned, it's like this. If it is only 2 sides supported, it will buckle something like this. Okay. But when 3 sides are supported, the buckling mode will be something like this, because these 2 sides cannot buckle. Simply supported, so they will not buckle. The free end will buckle. So the Kc value will vary accordingly. This formula is very similar to the formula for a beam. Only difference is that 1 minus nu square term is coming because of the width of the plate. So the Poisson effect is coming here. Okay. And T by B the whole square divided by 12 is nothing but that L by rho condition. Okay. Or rho by L condition, I would say. And these factors, here also you please go through this E.F. Brun, Analysis and Design of Light Vehicle Structures. Please note down this. It's a very important book. If somebody is interested, please refer this. Very informative, and a book which was written in long back around 1960s. So but it is the fundamental even now, because fundamentals of our science doesn't change starting from Newton's period. So E.F. Brun, analysis and design of flight vehicle structures is very important. Please note down this particular reference. It is available in the internet. And different end conditions of this particular condition of a plate is clear here. You will see here that depending on the end condition, there are different values for Kc. You can see here. Very, very low value, like 0.5 or 0.4 to 5.5 is coming. So the end conditions are very important. This is a condition where a hat section is buckling at different parts of a hat section is buckling. For example, this is a crown. You can consider this as a simply supported condition here. It will buckle like this. This will buckle like this. And after the rivet, you will see a free portion. It will buckle like a one and free condition, like what we have seen in the previous here. This is something like that. So this is the condition of a free edge beyond the rivet. So you can appreciate that when the rivet distance is far off. For example, if I'm giving a flange which is much longer than this, no, from here, if I make it very long, you can see that it has no meaning. When you really see that flange doesn't serve any purpose, it will simply buckle within sorry, I'm sorry, I pointer, lesser pointer. Okay. So this is the condition where we are having a very limited length of this flange. Sorry, again the highlighter has gone. Sorry. So this is the one. Okay. So I'm removing that. Sorry again. Now, when we come to the next one, this is a buckling shear. So you see that the pattern is something like a parallelogram. It is going into a parallelogram or a rhombus condition. Okay. And here, when you are going for a buckling under bending, how does a bending make a buckling? You know that beyond the neutral plane, there is a compressive region. Okay, in that region alone it buckles. So when we have a very long web, for example, in an eye section, the web is very long, it is likely to buckle even under very low stress. So this is a dangerous condition for an eye section. Even though we say that the eye section is very good in taking bending, the web also has to have a good strength, stiffness. Otherwise, the eye section will fail because of the buckling of the web under bending. Okay, this is a chart, non-dimensional compressive buckling stress, where we are having that N factor, what we designed in the Ramber-Osgood, similar way. We are having the effect of N here in the buckling. So if the early onset of yielding will cause a early buckling, that is what it is telling. Okay, this I am just written myself. Sorry for my handwriting being so poor. Now here I am just depicting a cross section where it is riveted. The shell is riveted to the end ring, and you are having a bending and shear force distribution. So you know that around this end ring, okay, there are regions where this bending is going to cause a compression here and tension here. How does that compression and tension really pass through this end ring is an interesting aspect. So where the compression is there, you know that the compression is going to happen by butting these two flanges. Okay. When the joint, a region where that joint is subjected to tension, for example, this area, it is subjected to tension. Okay. The joint will open there. What happens because of joint opening? The flanges will not be butting. So a portion of the load will go through the flange compression area. So there, even though the cylinder is uniform, the behavior of joint is different at different orientations. Compression is passing close to the hub, whereas tension is happening with a eccentricity from the hub. These kind of finer aspects we have to see. Okay, leave all these points. I'm just telling about the hat section. A hat section is having different members into it, crown, two webs and two flanges. Okay, and flanges are riveted. There's a free edge region. So these aspects can be designed with a you have the option to vary this W1, W2, W3, etc. to see that the hat section is properly designed. For example, if I am making this W2 too high, you know that it is going to buckle there. So you cannot make it too high. And the thickness of hat section is important. The height H is important. So these are the things. So this is basically a thing to tell what happens when the W width is increasing. Exponentially, the strength is going to come down. So because that T by B, the whole square, whatever we have seen earlier, is making the section weak when the width is increasing. Okay. Cladding correction. Aluminum alloy is given a cladding to see that the surface is protected. Pure aluminum is good in resisting environmental attacks. So cladding is given. Okay. What I tell here is the cross section of the thickness itself. So the T is a section of cross section of the sheet. A micron level cladding is given to see that the sheet is having a protection. Okay. But what is the effect of this cladding? What is the effect of this cladding? The overall, the thickness of the sheet, which is used to form the hat section, is becoming weak because of the cladding structurally. Because cladding will yield faster than the core. So accordingly, there will be a small weakening to the section to the extent of what is the cladding thickness. And local buckling stress of composite shapes. For example, these are the composite shapes. An angle, a T, a cruciform section. They undergo this kind of failures, buckling. So this kind of buckling is dangerous. That should be avoided. So what should be done? There should be enough of thickness. So when you build the thickness, you have to see what is the cladding there. And the thickness of cladding should be good enough for the environmental resistance. But it should not be making the section so weak also. So fixity points, these are all called fixity points. For example, in a cruciform, this is a fixity point. About that, it will start making the buckling mode shapes. Okay. Again, these are all different sections. This hat section I have already told you. This is something like a Z section. Okay. This G, etc. You please see that particular Brune book. There, all these things will be described there. Okay. Between two shells, there will be double splicer along with a T section between them. This is the way a shell is buckling. So between bulkheads, it will start forming this kind of mode shapes. I told you earlier, it is not a simply loaded condition like it, and in tension it will not have buckling, because tension is usually not a unstable condition. Stability condition doesn't normally arise on a tension member, but on a compression member it becomes unstable. So the instability is controlled by both longitudinal stiffeners as well as the bulkheads. Okay, so these are the bulkheads to see that the shell is not buckling. So when bulkhead is there, the shell will start forming shapes where the bulkhead is controlling the buckling. Bulkhead is controlling the overall buckling of a shell. I'm sorry, I have not drawn the axis. Axis is somewhere here, and the bulkheads are partition. Along the length. And you see here, when you take a section like this, when it is buckling, it will have mode shapes coming like this, mode shapes. Okay. And when you practically see a section strain gauge around the circumference, you'll see that after some time, the center of the this area will not start taking load. It will stop taking load. But the corner will start taking load. Okay. So really, when you see a development of this particular section, it will be something like this, okay, where you are having this section, the area where the corners are there. That corner, as I told earlier, corner is a fixity point. That will take much more compressive stress than the locations away from the corner. That is very important. So always we have to have corrugations. You should have this kind of shapes where you are having this kind of rectangular bends onto the stiffeners. Now, this is a very interesting curve. You know that Euler equation is like this: pi squared EI by L square, or pi squared E divided by L by rho the whole square. See, beyond a line, you will see that there is an effect of the yielding conditions for the strength conditions for the material. For example, when you take merging steel and mild steel, whether they will buckle together, they are having almost similar type of Poisson's E value or the Young's modulus and the Poisson's ratio. In such a condition, whether the merging steel or the mild steel, which will buckle first. Under Euler curve, you will see that it has no relation with respect to the strength. Okay, it is just depending on the E value and the geometric values like L dash and rho. So a beam, an Euler beam of merging steel and mild steel will buckle at the same load, theoretically. But there are cases where a beam which is subjected to post-buckling conditions, how does it survive? Or a shell subjected to buckling, after buckling, what will happen to it? In certain cases, post-buckling conditions has got some effects. Okay. So there, what really happens is, beyond a point, when you go on reducing your length L, whether it will go to a stress condition more than the compressive strength of the material, it will never go. So you know that at this condition, there's a termination point. Even if you are going for a length which is very short, the other mode of buckling or other mode of failure, like compressive failure of the specimen, will happen. There is an intermediate region between the compressive failure and the buckling failure. So that is the Johnson-Euler equation depicting these conditions. Okay. So it is the FC, and the crippling, all those conditions will happen when there is the failure stress is much more than the compressive strength of the material, or closer to the compressive strength of the material. Also, you have to have a redefinition of the failure. So this region is that. So it will be moving away from the normal condition of the Euler curve. Okay, these are all different conditions of Johnson-Euler curves. This also is available in that E.F. Brown's book. And non-uniform loading, this is what I was telling about the condition of, I'm sorry, I think I'm running out of time. It's already becoming 8. I'll go fast. So this is the locally loaded member. Sneha, can I have some more time? I'm sorry.
Yes, sir. 5 more minutes. You can take 5 more minutes. It's okay, sir.
5 minutes. Okay.
Yes,
So this is a compressively loaded member. This is a case where there's a loading on a pressure vessel where you are having a non-uniform deformation due to the geometric imperfections or the geometric discontinuities of a pressure vessel. And here it is a Sneha, if you want some more explanation, you have to tell. Otherwise, I'll quickly pass through this. You may not be able to understand what I'm telling. Okay?
Yes, sir. Yes,
there are some topics. If you are interested, I'll come back later. Otherwise, I'll leave it. These are all discontinuity stresses. And the region where you are having the non-linearity due to material is also coming here, because inner material is metal, outer is composite. Okay, and this is composite structure with a honeycomb core and metallic or composite facing, composite material facing. It is something similar to an I section. If you want more details about it, I'll talk to you later. Basically, these are all helping with respect to flexure and failure because of the compression. See, basically it is increasing the moment of inertia of the section, like an I section. Okay. This is the behavior of a bolted joint. What I want to tell here is the behavior of bolted joint is not really linear. There is a non-linearity here because of the pre-compression on the joint. If you want to detail about this, I'll come later. I'll stick to that timing. I'm sorry, I have taken more time earlier. Because otherwise, if I'm brushing through, you won't be able to understand. Okay, these are welding, riveting, and bonding. These are the different ways of joining. The different parts of a structure. Okay, here this is a segmented joint of a pressure vessel. Pressure vessels is in sections. How you join the pressure vessel is very important. It has got certain principles in which you define this particular joint. And when you have thermal contractions of the liners for a nozzle, these are all subjected to very high temperatures, something like 3000 Kelvin. And how the temperature diffuses into the backup, and there should be a refractory or the thermal protection system for the metals, because metal cannot withstand more than something like 150 or 200 degrees centigrade. Okay, so I'll leave these kind of explanations. These are all composite structures. Composite structures or the laminates are having different fiber orientations. You would have studied it. You want details, I will come back in your question and answer session, or you can refer the composite structures by Johnson. that book will be giving a details about many details about this composite structures. Now, basically, the kind of composite laminar stress strain relations are like this. It is similar to isotropic conditions, but only thing is E1, E2, and that E3 may be equal to E2 in certain conditions, like where you are having only two directional properties, and the third direction properties are similar to the second direction property. So E1 and E2 only will be there. Otherwise, practically this can be E3 also. Okay, this is a typical welded aluminum tank where you are having chemical milling. Chemical milling is to move away, remove certain material away from the weak spots of welding to gain advantage of the mass of that particular tank, so that otherwise everywhere you have to uniformly distribute the mass on the shell. So you have to optimize, and otherwise it will be a penalty for the rocket structure. See, rocket structures are normally a rocket structure will have around 4 to 5% of the metallic mass, and another maybe 4 to 5% of the thermal mass. So overall mass of a cryogenic tank maybe somewhere around 10% of inert mass may be there. So unless you control that within some 10%, there will be a penalty for the launcher with respect to the payload capability. Now, this is a rocket structure where again, like our fuselage, it is having bidirectional stiffeners. This is a fuel tank having a composite overwrap over a polyimide liner inside. So the overall mass of this tank may be, for this tank, the mass may be the combined mass of these two boys who are doing this work. It may be only something like 200 kg. Okay, this is a liquid engine. Liquid engine, this I have not described about. There are complexities with respect to this. I mean, the turbine and the pump of this cryogenic or the engines are working at around 44,000 or 45,000 RPM, whereas the liquid engines are working at around 6,000 RPM. And for example, our second stage of our PSLV, it is the horsepower of that particular turbo pump is nearly 2,500 HP, whereas the mass of that is maybe nearly 100 kgs only. So 100 kg of engine is developing around 2,500 HP. This is a welding. Welding has got a lot of versatilities. That's very important technique as far as our tank gauges and motor cases are concerned. Welding defects are very critical. We have to have non-destructive evaluations to qualify these welds. Structural dynamics is a very important area as far as structural engineering is concerned. Okay, we are having structural dynamic testing equipments. Okay. And this is a vibration shaker for a stage. A stage is undergoing a vibration in this direction. This is called a slip table. And the shaker is really going to from 20 Hertz to 2000 Hertz to see that different parts are vibrated. And if there is a vibration loosening, that also will be addressed by this testing. Okay. And additive manufacturing, all of you may be aware, this is a very important technique. We are trying to imitate whatever is there in nature. And nature is additively manufacturing the creatures it has got. All of us are additively manufactured from birth onwards or cell onwards to our present conditions, like that. But our we are trying to imitate what nature does. Okay, so a part of skull is implanted with some additive manufactured piece. This is feasible now. So the history of AM applications in timeline is described here. I'll see it later. Okay, and the composites, it is having a graded composite. It's a generic condition. Natural trend is something like this, a very, very uniformly graded thing is there in our bones. Okay, whereas we are trying to imitate in discretely graded conditions. Okay, and quasi-static loads and vibratory loads, these are all important. So you have to understand how a single degree of freedom system sustains and how it is to be designed. What is the critical condition of resonance, how to avoid it, and how that resonance beyond a particular level of root 2 times omega by omega n condition, that has to be seen. Okay, and then how it sees that the criticality of this point is avoided after this isolated condition. This is called the isolated condition beyond root 2. Okay. Okay, this free body diagram, this you have already learned in your beta classes. And as far as a beam is concerned, it has got different degrees of freedom. Okay, so thank you. That is the thing. So this is the way a launch vehicle or Saturn, which has taken human beings to moon, that is this shape, the mode shape. You can see how the mode shape is there for Saturn versus for a free beam. It's like a symmetric condition here. Why the mode shape is going like this? It's a totally asymmetric conditions. You just think of why the modal amplitudes of a heavier booster stage is lower. What is the reason for that? And why the balancing of mass or modal amplitude is important in a free body. What is a free body? These things you can get from E.F. Brunn's first book of Analysis and Design of Launch Vehicle Structures. That's all, Sneha, and your team. Yes, I'm all. Yes.
Yes, sir. So participants, if you have any doubt, you can either put your questions in the chat box or you can turn on your mic and ask any question. If you have any doubt, you can ask it right now.
Any questions? If I'm able
Which are the books that, which are the books that I can refer to get a better understanding of rocket technology and its potential?
Analysis and design, you know what I've told, E.F. Brunn, you can see, he has got 2 books, Analysis and Design of Launch Vehicle Structures, Flight Vehicle Structures, that you have to refer. Okay, then Composite Structures by Johnson. Okay, that you please refer. Okay, this is very important book, Analysis and Design of Flight Vehicle Structures and Analysis and Design of Missile Structures. These are the 2 books by, he is a very famous man. Based on his book only, our Saturn launcher was designed. Now, what I wanted to tell you is, design is very important, even though finite element analysis is helping us much more to detail about the kind of structural factor, etc. we can closely control. But the importance of design and the design approach what E.F. Brunn has made, okay, that is very important. And with that background only, we have to go to analysis. And nowadays, the analysis tools like ANSYS, Bacchus, all those things are there. But if you really see the kind of structural efficiency of Saturn, which was designed in 1965 or later, maybe 65 to 69. 69 was the launch of Apollo. That the advantage, what is coming out of detailed, the plant element analysis is only maybe 1 or 1.5% of our the structural mass. Earlier also structural mass was, if it was around 10%, now it would have become 8.5%, not to a big extent. But the advantage of analysis is you will come to know the problems of the design in much earlier condition. Okay, I'm going much beyond your question. Yes, any other question? And one more reference what you can make is for Snyder approach for the analysis of bolted joints with bolts beyond the bolt circle beyond the hub. That kind of condition is there. I'll get the exact details. I'll pass on this detail to Sneha. I'll pass on that references with respect to the flange joint designs. It's the Snyder's approach.
Thank you, sir.
Okay, if you guys have any doubt, you can ask it right away. If you have any issues with your mic, you can put your questions in the chat box.
Good evening, everyone. It's an honor to have got this opportunity to deliver the vote of thanks at this occasion. First of all, on behalf of Aagneya 2022 and ISRO GECBH Students Chapter, I extend my sincere gratitude to Mr. Krishnadasan, sir, for your wonderful session. Thank you for spending your valuable time with us, sir. The session was really informative and interesting. Thank you, sir. Also, I thank all the participants for your active involvement and presence throughout the session. Hope you all had a great time and got lots of information regarding the engineering of rocket structures. I hope the session was interesting to you all. The feedback form is given in the chat box and also the description box. Participants are requested to fill it. Thank you, everyone, and have a nice day.
Thank you very much. And
Thank you, sir. Thank you,
sir. Yeah, Sneha can pass on to me. Yeah.
Yes, participants, please do fill the feedback form. And yes, thank you so much, sir, for this wonderful session. It was really informative. Thank you very much.
Thank you very much.
Thank you very much. Thank you.
And all those that fill the form, you can leave the meeting.